Need that Y for number 5. Oh, this is our electron being attracted and repulsed. Alrighty. So, just as a reminder from yesterday, this was our Y, which had that nice force diagram that Courtney did. Alright. So I'm going to start off with going to my equation sheet and pulling out my electrostatic force and my weight equations. Alright. And then I know that the sum of my forces has to equal 0. I get that from my drawing here. So the way it was drawn, I have F sub P upwards plus a negative F sub G equals 0. So my electrostatic force must equal my gravitational force. Okay, Q1, Q2 over R squared equals mg. And I'm looking for, let's see, I want to know how far apart they are. So I'm looking for my separation, which is my R, right? So at this point, I could either substitute in all my values, or I could rearrange for R, right? Whichever way you find is easier. Which way do you guys suggest? Rearranging for R or substituting in my values? Okay. So I'll do that. 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Times charge on one electron, 1.602 times 10 to the minus 19th coulombs. And then my charge, 0.51 nanocoulombs. So 0.51 times 10 to the minus 9th coulombs over R squared equals the mass of an electron, 9.11 times 10 to the minus 31st kilograms times 9.81 newtons per kilogram. Ready to do the math, right? Seven is this one. Alright. Net charge, total mass, determine the number of electrons, determine the number of protons. And then yesterday that was the Y. That was nicely done for us. All right. So in this one, there really isn't any equations that we need because we're not talking about things interacting. We could kind of write, like the total mass is, all the masses added up, right? And because we need to start with those valid those equations. Let's see, what else could we write? We could write the charge total would be how do we want to put it? Number of electrons. Actually, we could say number of protons minus the number of electrons times the times the amount of charge that each one of them carries, right? And for that case, we could even say, okay, well, let's rewrite that mass total as the number of protons times the mass of a proton plus the number of electrons times the mass of an electron. Right? So, let's see. I'm told the net charge or the total charge, and mine's positive. Was yours positive yesterday? Yeah, so we know we have more protons than electrons, right? Because I have a positive net charge. So maybe I'll make a note of that. Number of protons is going to be greater than the number of electrons. That's just kind of to keep in mind, when I get all down into the weeds of this. And now, really, I think we can just do some filling in. Net charge 1.79 times 10 to the minus 15 coulombs. So coulombs equals number of protons minus number of electrons times 1.602 times 10 to the minus 19 coulombs. And then, what else they tell me? Total mass, 4.86 times 10 to the minus 23 kilograms. So we need a different color for this. Equals number of protons times the mass of a proton, 1.673. I've got two equations, and how many unknowns in each equation? There's two. So if I have two equations and I have the same two unknowns in both equations, is it solvable? Yes. Yes. So you can use whatever math method you would use to solve that. You know, maybe you solve one of them, like solve the bottom one for the number of protons, and then put that into the top equation. Personally, what I would do is use Wolfram to solve it, because I can put in both equations and separate them by a comma, and it would solve them for me. Wolfram Alpha. It's one of the solvers available on our links page. That's what I would do personally. What are you guys thinking of doing? How are you thinking of solving the math there? No? Okay. We ready to go on to number 6 then? Yeah? All right. All right. On to number 6. We got two positive point charges. The total charge in the system is given in microcoulombs, and it's positive. And each charge experiences an electrostatic force of that, where the separation is this. And they want to know what the two charges are. And we should notice that Q2 is larger than Q1. So if we look at our Y that was produced yesterday, we never got the direction on those forces from yesterday. That's what was missing. But we know that they... Oh
no, they didn't give it 12. They gave you the direction of the system.
Well, what do we know? It does. We don't have opposite charges, right? We have. Well, at least mine says both charges are positive. Is that what everyone says? Okay. So you should get this on about opposite attract. And then we need arrows. And 8. Sorry, just so somebody doesn't use that when they're studying and think, oh, that's 100%. It needs those parts. All right, but everything else there, I remember, is really good. So, all right. So I'm going to start from my equation sheet again with our equation for electrostatic force, right? That's how these particles are interacting. Then I know it tells me that Q1 plus Q2, oops, that's a horrible Q, is 58.0 microcoulombs. Right? And tells me a bunch of other stuff. How far apart, it tells me the R, their separation, it tells me the force, it tells me the K. Oh, so I can put in all that. So my force is 77. So I'm substituting into my equation up there. As always, let's move it over. Squared. Now I don't know Q1 or Q2, but I do know what the sum of them are. So again, oh, I hit that same kind of mathematical point where I have two equations, this one and this one, with the same two unknowns. So whatever mathematically you did for this is 6, for 7, the same math function for 6, right? Whether you use the solver or you substitute it in. I read it in my problem. It says that comes afterwards their separation is. Other questions on this one? Since all's left is the math. All right, so we're going to get on to number 8. Cool. All right, we're doing number 8. This is our spider hanging from the thread. And our thread is acting like a spring. So, and then the Y that you guys did yesterday is there. Now, my numbers are different than that 52.5, but I get their meaning on it. So I'm going to, let's see. Equations I'm going to grab from the equation sheet are my equation for the spring and the weight. So and just remember that negative is to indicate that the stretch and the force are going to be in opposite directions, but we've kind of taken care of that in our force diagram. We know for the spider that the sum of the forces equals 0. So the force of the spring minus the weight of the spider is 0. So the force of the spring equals the weight of the spider. Right? And then if we shift gears and look at the spring, that's why we needed the two parts to that diagram, we can continue right with that force caused by the spring. It has to be balanced with that weight of that spider. So we've taken it from one object to another. And I've already taken care of the directionality, so I can just do K delta L is the mass of the spider and the gravitational field strength. And I think they tell me my K, my spring constant, 65 newtons per meter. I know you guys like to substitute in right away. Was the increase in the length, so that is my delta L, which is what I'm looking for. The mass of my spider is 0.00017 kilograms. And I'm assuming this is not a space spider, so I'm going to assume it's on the Earth, so the gravitational field strength, and then I can just solve delta L. I read it in my problem. It's the spring constant given to me in my problem. Remember, that's one of the confusing things about this section. K, when we're talking about charges, is Coulomb's constant. K, when we're talking about springs, is the spring constant. Questions on number 8?